Hello again, and welcome to the fifth lesson on multithreading in C++. Today I'll introduce the multithreading methodology, which is the backbone of our course. We learned previously that multiprocessing is the system's ability to run multiple processes concurrently. This methodology allows the computer system to run countless processes efficiently. However, in multithreading, we focus on how to run each process efficiently within the multiprocessing environment. Let's take Apple Music as an example. When a process from Apple Music software is loaded into the memory and sent to the CPU for processing, the end user expects it to perform many tasks, such as displaying the software on the screen, establishing a Bluetooth connection, connecting to the internet, and more. These tasks cannot run consecutively, as we don't expect to wait for one task to finish before starting another. Therefore, they must run concurrently so we can have a fully enjoyable experience on the computer screen. And this is when multithreading comes into play. Multithreading is defined as the ability of a process to run multiple tasks concurrently. Tasks in multithreading are also called threads. Please don't confuse the word thread in multithreading with CPU threads. Now let's watch multithreading in action. When a process starts in C++, it first runs through int main. At this level, the parent thread ID is also called the root thread ID by the operating system. Now let's suppose that int main needs to call a thread that is independent of it, but runs concurrently with it. The scheduler will ensure the new thread has a CPU thread ID, a parent thread ID, and another ID called the child thread ID. It then divides the thread into chunks of bytecode that will be added to the time index, making them ready for processing. Notice how the parent thread ID of the newly created thread and the root thread ID of int main have the same value. This makes the green thread a child of int main thread. Let's take another example. If int main wants to call another independent thread that runs concurrently with it, the new thread would also have a CPU thread ID, a parent thread ID, and a child thread ID, then have its chunks of bytecode added to the time index. In theory, there is no limit to the number of children a thread can have, as long as the methodology of multithreading is maintained. Looking at the scheduler, similar behavior is expected on Microsoft Word and the Safari browser. Now coming back to int main, the root thread ID is always the parent to itself. Therefore, the root thread which runs in int main has the same value for both the parent thread ID and the child thread ID. Now the question you may ask is, can a child thread be a parent to other threads? The answer is pretty much yes. Suppose the green thread needs to call an independent thread that runs concurrently with it. The scheduler will give the new thread a CPU thread ID, a parent thread ID, and a child thread ID, divided into chunks of bytecode, and add the new chunks to the time index. However, notice that the child thread ID of the green thread is now the parent thread ID of the purple thread. This makes the purple thread a child to the green thread. This relation between parent and child threads make the index table still valid. All you need is to add the child thread ID section to it. Notice from the table how different threads that belong to a single process are running independently and concurrently with each other in a multithreading environment, while all processes are running concurrently and independently from each other in a multiprocessing environment. The combination of both multiprocessing and multithreading is called multitasking. In addition to the index table, you can imagine multitasking as something like this. One major difference between multiprocessing and multithreading is that in a multiprocessing environment, as you learned in Lesson 1, processes cannot share the same memory, nor can they open direct communication with each other. Instead, they communicate indirectly using inter-process communication channels. However, threads that belong to a single process in a multi-threading environment do share the same memory and can open direct communication with each other through this memory. This makes creating new threads much faster than creating new processes. It also makes context switching on a shared CPU core much lighter between threads on the time index than context switching between different processes. Nevertheless, for memory sharing to happen, there is a set of rules and protocols to allow safe communication and safe access to shared data, which is what this C++ course is all about. Here is a summary of what you've learned today. I am very excited to mention that the theory introduction of this course has ended here, and we'll start getting into coding from the next lesson. Any further theory will be explained at the right time as we move forward with the course. So join me for more, as plenty of practical examples are coming. But for now, I'm looking forward to seeing you in the next video.